So let us deal with these two problems. Both of these problems are asked to calculate the expectation and the autocorrelation functions of a random process. So let us see what I have done. First, for problem 7, we need to calculate the expectation of z of t. And this is just what we do. I need to say what we need to do is to calculate the expectation under the coefficient of theta. Also, I need to say that n1, n2, and theta are independent. So first we can put n1 and n2 out of the expectation to substitute them with their own expectation, etc. n1 and etc. n2. Then what we need to do is just calculate these two expectations. Then we find out that the cosine and sine functions have the period of 2 pi, and the theta is just from 0 to 2 pi. So these two expectations are just both 0. So the expectation of the whole random process is also 0. This is the constant. Secondly, we need to find this random process autocorrelation functions. This is just the expectation of z of t1 times z of t2. And first, we expand the equations and translate cosine alpha times cosine beta to cosine alpha plus beta plus cosine alpha minus beta, and etc. Finally, what we get is these four rows, and we can find for n1 times n2 because they are independent, so the expectation of them is just time it together like this, etc. n1 times etc. n2. But for n of t1, n1 of t1 times n1 of t2, or n2 of t1 times n2 of t2, because they are not independent. So what we get is just the autocorrelation functions of themselves. We can find the expectation of the cosine and sine functions. First, we find the theta and find out that the 2 theta is in the cosine or sine functions, because these functions have a period of 2 pi, and the 2 theta is from 0 to 4 pi, so the expectation of this part are just 0. What we get is just the right hand side of this 4 part, and some of them are cancelled. So finally, what we get is just like this, 1 over 2 times the autocorrelation functions of n1 times cosine omega theta plus 1 over 2 times the autocorrelation functions of n2 times cosine omega c times tau. Because these autocorrelation functions are just depends on t1 minus t2 or depends on tau, and the expectation of the random process is a constant, so the random process is wide stationary. The third question is ask us the autocorrelation functions when tau equals to 0, so we just substitute tau to 0. What we get is just over there. And the problem 8 is just let us to calculate the expectation and the autocorrelation functions of a random process following the Poisson distribution. First, we need to calculate the expectation, and what we do is just like the lecture about 3 did. We can say first we move e to minus lambda t and lambda t out from the sign of summation, and what we get in the summation sign is summarized sign is lambda t to k minus 1 over k minus 1 times k minus 2 times to 1. and this is just equals to e to lambda t, and this is cancelled with e to minus lambda t. Finally, what we get is just lambda times t, and this is the expectation of Poisson distribution. Secondly, we need to find the autocorrelation function of this random variable. We can see that is just here. What we need to do is to calculate the expectation of x of t1 times x of t2. Also, we know from the problem that if xt1 and xt2 are non-overlapped, they are independent, so we just make them non-overlapped. We let xt2 minus xt1. This is just independent with xt1, and then we plus xt1. What we get is just like this: the expectation of xt1 times the expectation of time t2 minus the expectation of xt1 plus expectation of x squared of t1. So what we need to do is to calculate the expectation of x squared t1. This is also done in the lecture 3. We can see from the problem A, we know that the answer of summation k times summarize k times lambda t2k over the k times k minus 1 times k minus 2, k from 0 to infinity is just equal to lambda times t times e to lambda t. Then we take both sides, with the both sides we take a derivative with lambda t, and what we get is just like this: k squared times lambda t to k minus 1 over k times k minus 1 k minus 2 is just equals to e to lambda t times 1 plus lambda t. And under this condition, we can easily calculate the expectation of x squared of t. This is just equals to lambda t times 1 plus lambda t. And use all the solutions into the autocorrelation functions equations. What we get is if t1 is bigger than t2, the autocorrelation functions is lambda t2 times 1 plus lambda t1. And if t1 is smaller than t2, the autocorrelation functions is lambda t1 times 1 plus lambda t2. And that's all. Thank you very much.